This is Mr. Craig, and I want to talk about the first day, or the introduction to thermodynamics, which is day 108. Today I wish to talk about the laws of thermodynamics, enthalpy, and specific heat. And again, these are all introductions. First thing I want to talk about are the different types of systems. The first type is an open system. And even though the notes say that it's open to the rest of the atmosphere, the reality is it's open to the rest of the universe. So anything that's produced in this type of system may leave the container and actually go into deep space if it has the capability of doing that. And we're talking reactants, the products, the energy. So that's an open system. A closed system is physically isolated from the surroundings. In other words, everything that's taking place with that chemical reaction stays within the container. Theoretically, none of that escapes, including heat. It's very, very odd to see something like that, but those are the two definitions. State functions. We're actually going to talk about a lot of different state functions over the next couple of days with thermodynamics. The first one that we'll primarily talk about is enthalpy, and you'll see that here in a few minutes. The other state functions that we will discuss deal with entropy and with, Gibbs free energy, and, let me look at the equation sheet real quick here. We'll deal with enthalpy, entropy, free energy, and that's it, just the three that we'll deal with AP Chem. All right, let's first of all talk about the law of thermodynamics. And again, thermodynamics is a little bit different in chemistry than it is for physics, and I'm not sure if the laws are actually the same, but let's go ahead and get into it. First law states that the energy of the universe is constant. In other words, all the energy that is available is being moved around. There's no such thing as someone being able to create energy or somebody being able to destroy energy. We just simply move energy from one location to the next, from one reaction to the next. So what we're working with is what we have. So there's nothing being created. So that's the first law. Second law states that if a process is spontaneous in one direction, it cannot be spontaneous in the reverse direction. In other words, we'll talk about spontaneity here soon, but I like giving this example. It's like saying, okay, we're in a classroom and the air is at room temperature, which typically is around 20 degrees Celsius or 70 degrees Fahrenheit. If I take an ice cube and I place it on the desk and I step back, what's going to happen to that ice cube if left alone? Well, hopefully you're going to say that it will melt. Now, I don't have to do anything to that ice cube. It automatically, spontaneously changes from a solid to a liquid based on the conditions of that room. That's a spontaneous act. However, if I leave the room as is, in other words, the temperature of the room, the desk doesn't change, that water will not change back into a solid on its own. So when we talk about something being spontaneous in one direction under a set of conditions, it will never be spontaneous in the opposite direction. All right, let's talk about enthalpy. Enthalpy deals with either heat or energy. So those are kind of the same topics or same terms there. When we talk about a change in heat, it's always accompanied in a chemical reaction. Whether it's a chemical reaction or a nuclear reaction, heat is either gained or lost. Anytime something's going on, as long as it is active, there's an exchange of heat. So a system can be defined as, that system likes to gain energy. We'll talk about what that is here in a moment. Or that system likes to lose energy. Enthalpy is a state function defined by the symbol H. Like energy, enthalpy cannot be measured directly. It is understood in terms of the change in enthalpy. So we look at the heat of the reaction before and the heat of the reaction at the end. Now this equation here is on your equation sheet. So actually, it's right here. I have it highlighted in the box here. That'll be the one equation that we may look at today. I'm not real sure if we have that in the examples, but what this is stating is that little sigma sign there means the sum of. So the delta H is the sum of the heat of the products minus the sum of the heat of the reactants. So whenever we look at a reaction and we say, that thing lost energy, in other words, it has less energy at the end of the reaction than when we started, we say that it is an exothermic reaction. Also, we can give the sign for that as a negative delta H. And I think we talked about this earlier on in the year. When we say that delta H has a positive value, that means that the products have more energy than the reactant started with. So the system, as the reaction went forward, gained energy. So anytime it's an endothermic reaction, we say that delta H is a positive value. So again, the equation states that it's the sum of the heat of the products minus the sum of the heat of the reactants. And make sure that we have that order correct. And if you notice on the equation sheet, it's always products minus reactants. We'll use that for a lot of our equations. There's one that will switch that, but we'll talk about that a little bit later on. But the ones that are on the equation sheet, those are really, really important because those are free game for the AP exam. Thermochemical equations. When we talk about a thermochemical equation, we'll talk more about this a little bit later on too, and again, this is an introduction. A thermochemical equation must be balanced and include all the states of each reactant product and list the enthalpy for the reaction. An example for such a reaction is given below, where we have nitrogen gas plus hydrogen gas yields ammonia. Pretty typical. The sign for this is a negative 91.8 kilojoules. Now, that's the heat of the reaction, the complete reaction with all the reactants and all the products that are being produced. Later on, we're going to talk about the heat of formation, or the heat of a reaction for 1 mole. And that's pretty typical because, and pretty significant because we'll talk about fractional coefficients here. Now, I know that some of you, when you learned how to balance equations, may have had some fractional coefficients to help you balance the equation, and there's nothing wrong with that. Just make sure that when you balance the equation that it's a whole number. Like you'll notice that the nitrogen has a coefficient of 1, the hydrogen here has a coefficient of 3, and the ammonia has a coefficient of 2. We never ever show fractional coefficients in our balanced equation until now. And we'll talk about that here in a second on the example. So what this statement is trying to say is that we can determine experimentally or by a set of given data what the heat of a reaction is based on the heat of the reactants and the heat of the products. So we would find out what the amount of energy that the ammonia has, and then we'd find out how much energy that the reactants have, the nitrogen and hydrogen, and we'd take the sum of the products, or the sum of the heat of the products, and subtract that from the sum of the heat of the reactants, and in that case we get a negative value. In other words, as we form ammonia gas, we actually lose energy in that process. And we'll talk about the mechanics of why that is here in a little bit when we talk about bond energy. So the formation or the destruction of a chemical bond. Also, if I do the reverse reaction, say I take ammonia and break it down into nitrogen and hydrogen, as we would expect, the sign should flip. So the value, 91.8, will remain the same, and that's kilojoules for that reaction. But when we flip the reactants into products, the sign will flip while the number remains the same. And that'll have some significance when we do some Hess's law equation in a day or two. All right, let's look on the back side. I've got an example. It says the complete combustion of butane gas in oxygen produces carbon dioxide and water. It is highly exothermic, releasing 2,845 kilojoules of heat per mole of butane. Here's the question. Write the balanced thermochemical equation using all whole number coefficients. Also determine the enthalpy change in burning 50 grams of butane. All right, so the first thing that we need to do, here's our answer, we need to write out the balanced equation. So here's the balanced equation. Also, what I want you to note is that in the problem it said that we had 2,845 kilojoules of heat per mole of butane. Why does the delta H have a 5,690 kilojoules of energy? Hopefully you notice, because we actually have 2 moles of butane. So whatever that coefficient is, however many moles we have of the butane, that's our multiplier for how much heat we have per mole of a certain substance. So what we want to do, first of all, we determined that. We wrote out our balanced equation. And also it wants us to determine the enthalpy in burning 50 grams of butane. Now, if it says that it is 2,845 kilojoules of heat per mole of butane, what do you think we need to do to the 50 grams for butane? Hopefully you're saying change that into moles. That's a good answer. Before we do that, let's make sure that we have our equation so that we have just 1 mole of butane. So in this case here, what we want to do is, since we have a coefficient of 2 in front of the butane, I want to divide everything by 2. Now don't round, keep it as a fraction. So in this case here, we've got 13 oxygen, 8 carbon dioxides, and 10 waters. So if you divide those all by 2, I will have a fractional coefficient for the oxygen, which is 13 over 2. That's okay, not a problem. It doesn't mean that we use 13 halves of oxygen in this reaction. It just means that's how much oxygen would be used. So we'd have some leftover oxygen, but we wouldn't use 7.5 of those. And then so also notice that our delta H has our correct amount of heat. So now what we're going to do is we're going to take that 50 grams of butane, convert it into moles. So here's our value. Again, the molar mass for butane, we have 4 hydrogens and 4 carbons and 10 hydrogen. So that's our molar mass here, 58.14. Take 50 grams divided by the molar mass. That will give you the number of moles. Then what we need to do is we need to take the number of moles, and multiply that times however many, let's see. Oh, okay. So we don't have a whole mole of butane. I'm sorry. I was looking around there. So I want to take the 0.86 and multiply it times the negative 2845. And for this 50 gram sample, this is how much heat would be given off. Now again, all combustion reactions do release heat. That's why they're exothermic. In other words, when we stand in front of a fire, we are absorbing the energy while the reaction is losing the energy. All right, last thing here. Measuring the heat of a reaction. We did this in General Chem. Enthalpy changes like the ones we just finished looking at can be determined experimentally. We had described enthalpies in terms of energy interactions between a system and the surroundings. Enthalpy changes can be determined by measuring the effects of the surroundings on the substance. Heat capacity. We'll talk about heat capacity. We'll talk about specific heat here. We'll talk about molar heat capacity. When we look at this equation here, Q equals MC delta T. We used this in one of our very first labs in General Chem. The Q here represents your heat, typically in joules. The M represents your mass, which is typically in grams. Skip over to the delta T. That's our change in temperature. In other words, the final temperature of the substance minus the initial temperature. So we always do final minus the initial. And then the C is our specific heat value, which has a very unusual unit. It's joules over gram degree Celsius. So if we talk about something being Q having a positive value, that means that we actually have an endothermic reaction and that the substance is absorbing energy. If we say that Q is a negative value, then that means that it's lost energy. So when you look at the sign for Q, because everything else would be positive here, well, except for maybe delta T, then we can determine what our value or our condition for Q is. Actually, we're going to talk about that here in a second. Let's talk about heat capacity. Heat capacity deals with the amount of heat that is required to raise the temperature of a substance by 1 degree Celsius. So some substances, like for example water, requires a lot more energy for that temperature to change by 1 degree Celsius because it has a much higher specific heat value. In other words, water is one of those substances that's able to absorb energy and hang on to that energy. Unlike metals that heat up really quickly and lose that heat really quickly. So when we talk about heat capacity, it's very, very similar to specific heat, but they have a little bit of a difference here. Molar heat capacity, obviously we would be talking about per mole for that heat capacity itself. All right, let's go ahead and look at examples part 2 to determine or to look at some of these problems.